It's a real honor and pleasure to welcome all of our audience to today's Solutions That Scale seminar. And I am very, very pleased to introduce our distinguished speaker this morning, Dr. Roger Aines, who is at Lawrence Livermore National Lab. Roger has had a spectacular career in various fields of energy. So I'll just give you a very brief background on Roger and then turn it over to him. He received his undergraduate at Carleton College and PhD in geochemistry at Caltech. And he has been in California ever since he came to Caltech for his doctoral studies. Roger has done amazing work in many fields of energy, including nuclear waste storage, groundwater cleanup, stochastic modeling, etc. He has spent much of his career at Lawrence Livermore National Lab. He was chief technical officer for risk assessment and environmental science division leader in the 2000s. In recent years, he was the carbon management program leader, and currently is energy program chief scientist. That's his current role at LLNL. And he's responsible for managing and leading the carbon initiative. And that's really the focus of his talk today. He is going to talk to us about doubling the climate benefit, turning California's waste into hydrogen. And before I sort of turn it over to Roger, I think the topic that he's going to talk about today is of great contemporary and current interest. And I believe that this interest is just going to grow exponentially with all the emphasis in Washington, in federal government on negative carbon technologies. So I think it's a delight and an honor to have Roger with us. And with that, Roger, take it over. After Roger is done speaking, then we will do Q&A. So wait till the end of the talk and then we will engage in Q&A. So Roger, over to you.
Thank you very much, Pramod. Thank you, all of you. I wish I was there in Irvine with you. Having gone to graduate school in Southern California, I can really appreciate the winter down there. So at any rate, I will share my screen again and we'll get rolling. At Livermore, we have a major program to look at how to clean up the atmosphere. And in the course of that program, we've discovered an important linkage to producing hydrogen. And that's what I'm going to talk to you about today. But I want to start by discussing the question of why we need to clean up the atmosphere. And I'll just be very brief here. That this is a summary of what the models tell us we're going to need to have in terms of carbon dioxide emissions into the future if we want to hit the kind of 2 degrees C targets that we all aspire to. 1.5 degrees C is even harder than this. And the answer is that we can reduce emissions, we can replace fossil fuels, we can be more efficient, but there will be a large amount of emissions that are either too slow or too difficult to remove. And of course, there's the fact that there's already too much CO2 in the atmosphere. And those two things combined cause that green area at the bottom, where basically if we want the math to add up, we need to get to net zero by about 2090 or so. But in order to get to net zero, we're going to have to actually remove carbon dioxide from the atmosphere. And the scale of this is almost unimaginable. That star in 2050 is sitting at about 10 billion tons of CO2 removed per year. That is twice the size of the world's oil industry. We move 5 billion tons of oil a year. We need to remove twice that much in CO2 by mid-century. So my laboratory looked at this and said, wow, that's impossible. We better start now. And we've been working on this for about 6 years. First, thinking about what are the real approaches that you can use to do this. There's some computer model approaches that are kind of fascinating, but not real. And then once you say what are the real ways to do it, how can we facilitate those? And that's what I'm going to be talking about today. There's three major categories of activities you can do to remove carbon dioxide from the air. First is encourage natural solutions, encourage trees, improvement of soil carbon. These are very, very beneficial from a lot of different angles and things that we should always pursue when we can. Then there's direct air capture, building machines to remove CO2 from the air. And this is very exciting because it basically addresses the problem in the simplest possible way. If the problem is there's too much CO2 in the air, let's build a machine that removes it. And so legislators understand this, policymakers get it, technologists love it. It's horrifically expensive at the moment, but we're hoping to do much, much better. In between is the thing that I'm going to spend most of the time talking about today, and that is biomass solutions, which are kind of a hybrid, where we use natural solutions, growing plants to remove carbon from the air, but we're not actually going to deliberately grow the plants. We're going to use all the waste that is resulting from our otherwise, our other industrial use and home use of biomass in trash and industrial waste and agricultural waste. So let's look at these briefly, each of these three things. Trees and soil, first of all. Who doesn't love trees? It's a great option, and it gets an enormous amount of attention because we really should do a better job of that. But let's look at soils first, because soils are frankly the biggest option out there. Because of our bad agricultural practice, which includes this young man plowing his field sometime around the turn of the last century, we've lost a terrific amount of carbon from our agricultural soils around the world. And this plot by Sanderman, I think, is one of the great plots of the climate age. They looked at all the agricultural soils that they have data for. And it turns out that most people who monitor soil measure carbon in it. Everybody has an agricultural program. The black areas are the places where there's no data. And they compared how much soil has been lost from the agricultural fields to nearby fields that aren't used for agriculture. So that's how they got this loss. And everything in red there is massive losses of 50 to 100 tons per acre. And that is something that has happened over a long period of time through these bad practices. But the question is, can we reverse it by good practices? Can we put it back? If we could, it's the equivalent of 487 gigatons of carbon dioxide. If we could remove that amount from the atmosphere by putting it into soil today, we've done. We wouldn't have to do anything else, but we can't. It's just too slow. Second thing that people love is trees. And these are some redwood trees here in California. And they're about reaching their maximum rate of carbon removal here. Those are about 40-year-old trees. And at that point, they're really removing a lot of carbon from the atmosphere. But up until that point, they're relatively slow. Of course, brand new trees are removing tiny amounts of carbon each year. But that's not the only issue with planting trees. A big one is, where can you plant them? Is it a suitable place to actually grow trees? You can't grow trees everywhere. And then these other issues of sort of leakage and additionality, which sound like technical terms, but they're really very important for, are we really actually removing carbon dioxide from the atmosphere? It's one thing to make a bold statement. It's another to really reduce the amount of CO2 in the air. Durability is a big deal for trees, especially here in California. We've all seen the wildfires. This is the amount of carbon that's emitted by those wildfires up to 2020. I don't have last year's numbers yet, but that's staggering. That's considerably more than our industry in California emits. Obviously, if you want to use forests as a sink for carbon dioxide, you have to protect those forests. You can't let them burn. And this is becoming a bigger and bigger deal. It used to be only California. Now it's California and the West and Colorado. And at some point, we're going to see eastern wildfires. It's going to happen. But another topic that is really important here is that the advocates for using massive amounts of trees want to plant trees and basically reforest a lot of places. But in many places, including here in California, a continuous forest is not the natural ecosystem. And if we want to pay attention to biodiversity and basically having an ecosystem that we appreciate, we have to understand that here in California, these oaks openings, these mixed grassland oak pastures are the correct ecosystem for this land. And actually, because of the soil carbon that is stored in these systems, they actually store as much as if you covered it with a forest. But you can't just say, oh, let's go plant pine trees on this and solve the problem, although that's what Germany has done. To my mind, that's too simplistic an answer. Leakage is a really important thing. There's a lot of promises not to cut timber, and you will see these in all kinds of carbon crediting schemes where somebody says, I won't cut my 100 acres of timber, but it doesn't make any difference at all if somebody next door does cut their timber in order to meet the demand. We have to reduce the demand for timber if we're going to use that as a way to manage carbon. And unfortunately, I think using wood to build things is an important way to have a low carbon economy. So we can't just say we're not going to cut trees to have timber. We have to figure out how to stop cutting trees for purposes that aren't beneficial to us, which, you know, a lot of what's happening in Brazil is forests simply being cut down so they can have grasslands to grow cows on, which so it's a double whammy. If we take into consideration all of these things, could we really manage our forests very well? Could we protect the ones that we have today? The best estimates, I think, are that we could get about 3 billion tons of forest-based negative emissions per year in the future. That's of the 10 billion tons that I said we need in 2050 and 20 billion tons that we need by the end of the century. So forests are important, but they're by no means the entire answer. The second thing that I'm not going to dwell on here, but I will touch on for completeness is the idea of direct air capture. These machines like this one that's running in Switzerland that basically remove carbon dioxide from the air. Some incredible engineering here. This particular company, this is Climeworks. It was built by a couple of students at ETH who were literally taking chemical engineering classes as undergraduates and said, that doesn't look hard. Why don't we make a company that does this? And they do, and they're being very successful. The amazing connection here is with geothermal power. Geothermal heat, a lot of it is available in some places around the world. And it turns out that these direct air capture facilities really need heat. They don't need electricity. And the heat is used to release the carbon dioxide from the sorbent that they've used to grab it from the atmosphere. And so if you have a source, a low carbon source of heat, that's the best place to build a direct air capture facility. And that's what Climeworks has done with this new facility that just came online in Iceland. This is a 4,000 ton per year direct air capture facility powered by geothermal heat, which Iceland has an enormous amount of. And this is going to be a real growth industry for Iceland. Obviously, 4,000 tons a year isn't very big and we need to grow that, but they're working on that. And I have a lot of hopes for that. It's going to be an important contributor to the overall picture. But as you can tell from all the engineering, it's still going to be expensive. With that, let me come to the main part of the talk here. What if we could capture the carbon that is being stored in biomass and use it to produce things like hydrogen? An important caveat here is that I'm only talking about using waste biomass because there's an enormous amount of waste out there. And probably in the United States, there's on the order of 500 million tons of organic-based waste. In California, we've done a good accounting and we know there's about 45 million tons. So there's an enormous amount out there. We don't need to think about growing new crops or cutting down forests to do this. We're going to use the stuff that already we're letting burn or decay. And I kind of feel like I'm bringing coals to Newcastle to come to Irvine to talk about gasification. But so I won't talk much about the details of the technology here. I'll mostly talk about the impacts. But what I'm talking about basically here is a direct single stage gasification with water gas shift, so that you maximize, you basically turn all the carbon monoxide into hydrogen and carbon dioxide by reacting it with water. And so what comes out the other end of it is almost a pure stream of carbon dioxide and hydrogen, which is a great way to use this, because now we have a valuable energy product, the hydrogen, and all of the carbon has been separated into the form of CO2 that we can permanently store. The challenge here, all of these things exist. Everything on this figure has been done at large scale, but no one's ever strung it all together. Biomass, autothermal gasifier, not using any external fossil fuel, making the hydrogen and then capturing the CO2 and storing it. So very hopeful, since all the individual steps have been done, that you'll be able to do all of these together. And forest waste is a really great place to start in California. Because of the forest fires that we've had, we're now thinning forests, which is the process you see going on here, where small trees are removed in between the big trees that are allowed to grow faster. Why is this a good idea? Well, it turns out that when you let the big trees grow faster, just like those oaks openings that I showed you earlier, you actually remove more carbon than having a highly competitive brushy landscape that doesn't have big trees. Big trees store a lot of carbon, so you want to let them get big. And this also turns out to be a great way to control fire, because the big trees are not as likely to burn. And in this year's horrific fires, particularly up in Plumas County, what we saw was the places where this thinning had occurred, the firefighters were able to set back fires and stop the motion of the fires. There was enough fuel reduction here that a backfire would work. So this is something that the state is pursuing. And the question is, what happens to all that wood? Well, today, believe it or not, they pile it up in the forest and they burn it. Oops, not a great idea for a lot of reasons: air pollution, carbon use, obviously. And frankly, it's, not obtaining value from something that we could get a lot of value from. And we've estimated that in California, there's a lot of this available, particularly in 2045. This figure shows our estimates for then. And what you see in red is the forest material, mostly from that thinning process, but also from ongoing logging that's being done. And that's mostly in the northern part of the state. But that's not the only form of organic waste in the state by any means. Agricultural waste you see in yellow in the Central Valley. Do you know that we throw away 1 million tons of almond shells every year? 1 million tons. I like my almonds, but I'd like to see those shells used for something. And there's trash in blue in the southern part of the state where you all are. A lot of people, you have a lot of trash, and trash is about 70% organic waste typically. And the last thing is the sewage, which you might think is a bigger carbon source, but it actually isn't. There's not that much carbon in sewage. But you add all these things up, and there's about 50 million tons today and about 58 million tons in the future. So this is a huge source of organic carbon. And if all of that carbon was converted into CO2, that would be about 100 million tons of CO2 that a few years ago or recently was in the atmosphere. And if we took it out through these processes and then permanently removed it from the atmosphere, that would be a true negative emission. That would be a big contributor to that green plot that I showed you at the beginning of the talk. And this has become a real mission for us at Livermore. We started making these plots and looking at these things, and we went, holy cow, that is a huge target. Let's figure out what it looks like, what it costs, and what the implications of this are. One of the first implications is that we've been thinking about biomass in the wrong way. For hundreds of thousands of years, we think about biomass as an energy source. Well, if we look at the biomass sources that I was just talking about, and we start comparing, if we made them into some of these liquid fuels or made them into a pellet feedstock, for instance, they don't have very much, they're not very valuable. But if we look at the amount of carbon in them and say, what's the CO2 value of those fuels? That's what this plot shows, is as a function of an increasing carbon price, what is the value of those biomass fuels? And we see that the CO2 value rapidly outstrips the energy value at, certainly at around $50 a ton, which is the current carbon price that's pretty uniformly available in the United States. And at a price of $100 a ton, which I regard as a reasonable long-term value for carbon dioxide, we see that the CO2 value of biomass is on the order of 2 or 3 times the energy value of it. So we need to be thinking about managing these sources as carbon sources, not as energy sources. Not that we wouldn't take advantage of the energy, but the most valuable thing is the carbon. And this comes back to another trope that you'll hear a lot, that it's hard to transport biomass, that you can only transport biomass 50 miles to a plant. Boy, I can't tell you how many times I've heard people say that. And it's probably true when you're doing it for energy purposes. But this truck full of wood chips is really not very useful for energy, but it's a terrific carbon source. That truck is 50% carbon by weight. Well, the contents of the truck anyway. That's terrific. And you can afford to haul that a very long way. And so this really changes the perspective on how you think about using biomass. It no longer has to be an entirely local process. And this was a surprise to us. When we set out to analyze this, we thought we were going to be, we really thought we were looking at small scale processes that could move up into the forest and be close to where those clearing operations that we showed you are. Not true. Not that you couldn't do that, but those are actually a lot less efficient because of the capital cost of building small facilities versus building large facilities. So California can use biomass gasification explicitly to solve 2 problems. And this is part of the analysis that we conducted here, is to say, with all these sources that we added up in California, how much do you spend on drying and grinding it, gasifying it, cleaning that up, separating the CO2, and then compressing and transporting the CO2 for permanent geologic storage, which I'll come back to in a minute, and then liquefying the hydrogen. Now, there's a lot of different ways that you could deal with hydrogen, but for the purposes of this analysis, it turned out that liquid hydrogen was the most valuable product. So we calculated it in that way. And for all of that waste that I showed you in the bar graph that was showing you the whole state, we believe that we could obtain about 3.8 million tons of hydrogen per year and 85 million tons of carbon dioxide per year. So this is a dramatic increase in the amount of both of those that are currently available in California. Now, this direct biomass gasification, actually taking wood chips and turning them into syngas and then processing the syngas, is one way that you can think about biomass utilization. Another way that I want to briefly touch on is the thing that's going on out in the Central Valley extensively today, and that is anaerobic digesters. Actually, every sewage plant has one of these. And in an anaerobic digester, you're basically making methane. About 2/3 of the carbon molecules end up as methane, and 1/3 of the carbon atoms, end up as carbon dioxide. Well, if you just put that into an engine to make electricity, as many of these facilities do, then that ends up, you just end up exhausting all of the carbon as CO2. But what if you separated that CO2 ahead of time before you used the methane as a downstream product? That's a really simple separation to do. And that's another thing that the state can and should do to improve that market. It's a really simple way to remove carbon from a biomass source from anaerobic digestion. So what does this mean in terms of the hydrogen market? I want to talk about carbon intensity of hydrogen. In the current discussion around climate appropriate hydrogen. There's a lot of discussion about electrolytic hydrogen with good reason, that basically by powering this with renewable energy, we can make hydrogen that has a carbon footprint of approximately 0. I don't want to talk too much about, the small percentage. When you run the LCA, you'll find that these things vary by a little bit, but do a first approximation, it's got a footprint of 0 carbon per kilogram of hydrogen. What are we doing today? Almost all the hydrogen in the country today is produced by what's called a steam methane reformer, an SMR. Every major refinery you look at has got SMRs running it, making hydrogen to help refine the gasoline. And that facility emits about 7 kilograms of CO2 for every kilogram of hydrogen that it makes. Well, the companies that do this are looking at this and saying, well, okay, we could do better. We could capture that CO2. And when you do that on a conventional steam methane reformer, which is basically a syngas unit, you can get about 2/3 of the CO2. It turns out that it's a lot of different burners in a system like that, a lot of different sources of CO2, so you can't actually grab it all, but you could reduce it by quite a bit. And there's several plants operating like this, including a full-scale one in Louisiana that's demonstrated that this works. Most people look at that and say, okay, that's better, but that's not our target. We want to get down to 0 that we can do with electrolytic. Well, it turns out if you design a steam methane reformer for carbon capture, you can get pretty close to 0. You get down to fractions of a kilogram of CO2 per kilogram of hydrogen emitted. And this is basically by reducing all those different heat sources. But you're still emitting a little bit of carbon dioxide from a facility like this. And this is assuming you're running it on fossil natural gas. What if we ran it on that biogas that I just showed you coming out of that anaerobic digester after we removed the CO2 at the anaerobic digester? So we've already removed 1/3 of the carbon dioxide from the energy stream before it gets to the steam methane reformer. And then if we do this full capture on the steam methane reformer that captures 90 or 95% of the CO2, we now end up with a net negative carbon intensity. This is pretty exciting and relatively simple to do, because this is all technology that is you know how to do it. And there are some companies looking at running hydrogen production with biogas, although there aren't many biogas facilities that are capturing the CO2 from it. So this very low intensity is not going to be available immediately, but it's technologically very straightforward. This is pretty cool. What this means is you're making hydrogen that is removing carbon dioxide from the atmosphere while you make the hydrogen. But it's not the best we can do. If we went back to starting with the wood chips, where we basically now capture all of the carbon that was originally in the biomass, separate the hydrogen, and permanently store that carbon dioxide, we now end up with a carbon intensity of -20. We're removing 20 kilograms of CO2 for every kilogram of hydrogen that we make. Now, this is the kind of win-win that we've got to have if we want to make this whole thing work quickly and inexpensively, and basically with a lot of societal acceptance. There's a lot of people who would look at this and say, yeah, that's a future I'd like to see. I want to have hydrogen. I want to have the benefits of all the things that a high intensity fuel can give us, and at the same time, clean up the atmosphere. There are a couple companies now that are designing facilities like this in California, and the state of California looked at this and said, that's a great idea, particularly with regard to forest waste. And so there is now a $50 million budget item that they're figuring out just how to distribute it, but a $50 million investment in a demonstration facility to basically build a facility that does this work and demonstrate this outcome. Well, you never want to trust academics on cost estimates, but we did our best, went to the literature and said, how much would it cost to build these facilities? And with no regulatory support. You see the black line up at the top, and that black line, the cost goes down as you get to a bigger and bigger plant, and about 500 tons per day is the size of a big steam methane reforming plant, size of a big plant operating, making hydrogen today. And with no regulatory support, that is more expensive than the current SMRs today. But there is a significant amount of regulatory support. Basically, today, if you were making this hydrogen in California, you'd be getting about $200 a ton in combination of low carbon fuel standard and 45Q federal credit for putting the CO2 underground. At $200 a ton, we now see that you're making almost $2 a kilogram. It's not costing you money. Basically, and that's not including, excuse me, that's not including the cost of selling the hydrogen. You're producing hydrogen where you're already making money before you even sell the hydrogen. So this is why companies are looking at this and saying, oh, wow, we need to get into this. And of course, it's still a challenge to get to actually build a facility like that. And part of the challenge is the resource constraints. So let's look at what it really takes to make a 500 ton per day hydrogen plant. Well, if we wanted to make it with electrolysis, then it's going to take the equivalent of about 50 square miles of solar panels to provide that amount of energy for an electrolysis plant. We can certainly do that. This is about 7 square miles of solar panels, which is the biggest solar farm in California today. It's up in the Carrizo Plain. But you could build a 50 square mile solar panel farm if you need to, but obviously it's going to be a land use challenge. Second thing is to use the biomethane, like I showed you. Well, this is a bigger problem. It's an attractive idea, but to build this big 500 ton plant would take 2/3 of the United States biomethane production just for one plant. That's obviously a problem, even though with book and claim, we currently do distribute methane and credits for methane all over the country. Most of the methane produced by anaerobic digesters is used in California as fuel. And of course, it's not the actual molecules, but you get credit for it. But you'd have to really scale that up a lot in order to run that kind of biogas fuel facility that I mentioned. And for using forest wood waste to build a plant that big, you basically need a unit train every day, or basically 5 days a week. It's about 2 million tons of wood a year. We have plenty, we have lots of wood. We have, like I said, we have 50 million tons of material like that available in California. But to build a facility, you're going to basically need a source that can supply you that amount of wood. And that turns out to be the problem, that the contracts that are available today from the forest are small, short-term contracts, and nobody can go out and enter into a contract to buy 2 million tons of wood waste a year, even though the state intends to produce it. State recognizes that's a major problem, and they're working to solve that. The first plants that are being designed right now to do this job, interestingly, are not using wood waste. One of them is using trash, because you could sign a contract with Waste Management for 20 years to get their trash. It's like a known reserve in an oil field. They got a bank loan to build that facility, which, by the way, they're building in Reno because it's hard to build things in California. The agricultural waste is relatively easier, but you still have to accumulate multiple sources. Even, the almond shells, that 1 million tons, is distributed up and down the whole Central Valley. So there is still a supply issue. We're all familiar with supply problems today. Anyway, those are the kinds of things that have to be worked out in order to make this future a reality. But the fact that there's so much money on the table and so much environmental benefit means the developers are interested, the state's interested, the federal government's interested. This is one of those win-win-win solutions that people are going to try and make happen. And there's another issue that has to be resolved, and this is why a geologist is talking to you about this. All that CO2, I was talking about 85 or 100 million tons a year of CO2 has to go back underground. It has to end up where we took it out of to begin with, because there's simply nothing else to do with it. Even if we grow all the trees and make the soil absorb CO2 as fast as we can only get a fraction of the amount of carbon dioxide that these kind of facilities will emit. The good news is that when you put CO2 back underground, a mile underground, it ends up looking very much like oil. It turns into a liquid. It has the same density. It has the same viscosity as oil. It'll stay in the same rocks that have held oil for millions of years. And we all know that oil can leak out of rocks. We see that happen in California, but it's hard to get it out from 500, let me get my numbers right here. It's hard to get it out from 5,000 feet down. And so when we put CO2 underground, we think it's going to stay there. And people like me have studied this for 25 years. There's been an enormous amount of investigation around the United States in experimental programs. We put 14 million tons underground in a number of places. It works. It can be done safely. There obviously need to be good regulations, but we have the most strict regulations in the world. The other piece of good news here is that the sunset of the oil age can be the dawn of the storage age. It's the same people, it's the same jobs, it's the same lunch trucks that are needed. And so this is one of those things that can be an important part of an equitable transition, particularly in the Central Valley of the United States, California. Geologic storage is something that not everybody is familiar with. So let me just spend a moment on that. There are two extensive regulations that cover this. One federal, covered by the EPA, and one the state, from the State Air Board. They basically require that the CO2 be put at least 3,000 feet underground, where it turns into a supercritical liquid. I don't tend to use the phrase supercritical in public audiences because if it's bad, it's critical. And if it's really bad, it must be supercritical, right? But we all know we're talking about a phase, not a condition. Stored underground, it basically goes into sandstones that look a lot like the beach sand you'll see at the beach, where there's space in between the sand grains, and the CO2 fills the space that is left in between those grains. This requires good regulations. It requires building codes, but those are all being put in place. And it requires really strict regulation. And that's frankly something the state of California is struggling with. Who's going to be the active agency? Who's going to make the rules here? And there's a lot of environmental organizations that don't trust California regulators. And so this has become a fractious topic. I think it's something that's going to happen, but it's something that it will be highly contested in the state of California. But the simple fact of the matter is that rather than saying we can live without it, we need to say, how do we understand how to do it well? How do we do it safely? I like to say this is about as dangerous as building a 20-story building, about as complicated as building a 20-story building, which we wouldn't do without good regulations, without universities that train good architects, without materials that were rated to do those jobs. These are all the same things that we need for carbon dioxide storage. There's one other environmental issue that I want to spend a minute on, and that I was a little glib about the gasifiers that we do this with. But there's really, to my mind, a geologist's mind, there's two kinds of gasifiers out there today, good ones and bad ones. The good ones are the ones you see on the left, which are basically single stage systems where everything is contained in one system. And the bad ones are the ones on the right, where you fundamentally burn the biomass in the right-hand system to heat up material, which is then used to gasify biomass in the left-hand side of the system. And the problem here is what that means is you have a smokestack on that system. In the orange, you see that combustion products coming out. And let me tell you, in the Central Valley, that is not popular. They are not fond of biomass burning facilities out there that are nasty and dirty and add to air pollution, which is already terrible in the Central Valley. And if you go out there and say, I'm going to build another facility that burns biomass, the answer is no. We have to have these facilities, these single stage gasifiers that essentially have no emissions at all, where all the gaseous effluents go through the treatment system. Everything is turned into carbon dioxide, hydrogen, or solid products which can be safely stored away, but they're not adding to air pollution. So we studied all of these at the lab and did a report for California, which is called Getting to Neutral, which if you just Google Getting to Neutral, you'll find it as easily as trying to look at this link. It has a lot of the information that I just talked about. And the conclusion that we reached is that California can use these negative emission schemes to help reach net zero by 2045, and that the amounts that we need are readily available if we use all the tools in the toolbox. We looked at natural and working lands, trees and soil, and we said we can get about 25 million tons a year. And I have to tell you, that was generous. We assumed that everything went right, and things don't tend to all go right. But if they do, we can get 25 million tons a year. Part of that is because we never deforested California. Unlike some places like Tennessee or Maine, where they're rapidly reforesting and storing a lot of carbon. The waste biomass conversion is going to be can be a big part of our future. We think economically, it looks like we could get on the order of 80 million tons a year from that process, while generating other benefits like making hydrogen. And that leaves, for a total of 125 million tons, that leaves us a relatively small contribution from direct air capture, which is the most expensive. When we look at a cumulative distribution plot of this, or a supply curve, basically for a supply curve, what you do is you say, I'll start with the cheapest source of the thing I want, and then keep adding in next most expensive until I get to the amount that I need, to the 125 million tons that I need. And so the supply curve that we derived for California, the cheapest supply curve, is shown here. Natural solutions, on average, about $11 a ton. Of course, you're going to do as much of that as you possibly can. Then in orange and red in the middle are all these biomass solutions. And in each case, turning the biomass into hydrogen was the most valuable way to do it. I'll come back to that in a minute. At the end, you see the contributions from direct air capture. We estimated that in the long run, direct air capture could get below $200 a ton if there were a lot of facilities built. This basically means building 30 to 40 full-size facilities around the country, or around the world even. Those are 1 million ton per year facilities. And remember that I told you the biggest one in the world today is 4,000 tons a year. By the time you build that many, you can get the cost down from the $500 or $600 that it is today down to $200 a ton. Well, the biomass solutions in the middle are by no means the only way that you can treat biomass. We love hydrogen because it's such an efficient way to use the whole system. But you can take all these organic sources and then you can use them to make a lot of other things. Hydrogen, you could just burn them to make electricity and capture the CO2 from that. You can use them to make liquid fuels. That plant that I told you about in Reno is actually making aviation fuel. You can make biochar, you can make renewable natural gas, which the PUC is considering a rule to require the California utilities to buy 15% of their natural gas from sources like this. So there's a lot of other things that you can do with the biomass, and generates a lot of other supply curves. The hydrogen just ends up being the cheapest one, but we basically added all these things up, looked at the entire system and said, how did that work out? And you see that on the right is another one of the supply curves where we said, instead of making hydrogen, let's use it to make direct electricity. And it's a little more expensive. You need a little more of it because it's not as efficient as making hydrogen. And so you end up needing more direct air capture to fill in the 125 million tons. But the answer is there's a lot of ways to do this. It can be locally derived. There's nothing magical about making hydrogen. It just ends up, I think, having the best political support overall. Hope I've convinced you that hydrogen can be an important part of a big tent solution to our climate problems. And I want to encourage you that we need to embrace technologies that both replace fossil fuels and clean up the mess that we made in the air. And because of the size of the problem in both of those, we have to do them together. We have to pursue them both now. We have to go fast. We have to figure out how to be efficient We can't be perfect. We have to be good enough. Thank you very much.
Roger, thank you for that wonderful, instructive, inspiring talk. Some questions are coming up, so I'm going to start posing you the questions, and you can take your, give us your wisdom. Okay, what about problem of CO2 becoming carbonic acid?
It turns out that underground, there's the groundwater is almost always saturated with carbon dioxide. There's a lot of carbon dioxide in geology, and so it's already there. When I first started studying this, I thought it was going to be the full employment act for geochemists. I thought we were injecting an acid into rocks and it was going to dissolve the rocks. It was going to be really exciting. Nothing happens because it's already equilibrated with CO2. I think there's a lot of reasons to be, that's a first order answer. There's a lot of reasons to be a little more cautious. You may release metals, you may be more acid, but it's not a large problem. It's a relatively manageable problem.
How do you prevent possible leaks? The questioner is thinking of the Lake Nyos disaster emission of gases from under a lake in Cameroon that suffocated people.
So the first thing to recognize is that this is done all the time, all over the country now for enhanced oil recovery. There's a lot of work done. And like any oil operation, there are occasional leaks, and they know how to control those. Basically, you call up Halliburton and they come out and plug your leak for you. In general, the problem with Lake Nyos was that it was a deep basin that filled overnight with CO2 from a volcanic eruption. We all know how dangerous those can be. And was an unusual situation, which is not to say that we should trivialize that. There are things like basements and things that can have CO2. But in general, that's a design problem and to a certain extent a monitoring problem. And like the 20-story building, you don't want to go out and build it out of popsicle sticks. You need to have all of those things correctly done. And my assessment is, after 25 years of studying this, that we can do that safely.
What do you do with the leftover ash from the gasifiers?
Good question. I think it fundamentally probably goes into a landfill. There are a lot of people who would like to extract the minerals and use that as an agricultural amendment, and I certainly would cherish that. But it may be too hard, but it's a small enough volume that if it goes into the landfill, it's not bad.
Okay, this goes back to your slide 22. I don't think you need to show the slide, but the question is, how do you go from -7 to -20 carbon intensity?
So at -7, you're using biogas, and that biogas is not as efficiently produced as the if you're doing direct gasification of wood. So you're not capturing all of the CO2 in the SMR, and the well, I'm not answering this question very well. Basically, the direct gasification is it ensures that 100% of the carbon ends up being captured, whereas it doesn't get captured in the biogas use.
Thank you. This is back to safety question. Are there any long-term studies of safety of large-scale underground CO2 storage?
As I say, this has been used in enhanced oil recovery in the central United States since the late 1950s, early 1960s. Not quite the same, since they don't deliberately pressurize those fields. They're always extracting oil when they push in CO2. Basically, the CO2 is used as a solvent to remove more oil from the rocks. The longest study of exactly what I'm talking about is in Norway, at the Sleipner project in Norway, which is damn near as old as I am. No, that's not true. It's been operating for 25 years. It was operating before I started working in this field, and they've been putting 1 million tons underground there every year. In the United States, there's about a dozen large-scale projects now that have more than 4 or 5 years, and a couple with a decade of experience with them. It's been, frankly, very encouraging. It takes good design. You have to pay attention to it, but there have not been any problems. There have been no leaks. And, basically it's one of those things we say, okay, if we do this right, we can do it.
Next question is questioner is curious about what you think of the biggest challenges in using ocean instead of land for carbon capture.
So the interesting thing about the ocean is it's capturing the carbon right now. Most of the most 2/3 of the carbon that we emit actually ends up in the ocean. The rest ends up adding to the carbon in the atmosphere. So it would be wonderful to be able to somehow engage the ocean. And there are some people looking at some thoughtful ways to do that, including growing large algae, seaweed, try to use that as a carbon source. There are people looking at changing the carbonate balance in the ocean, where basically by adding bicarbonate to the ocean, you improve both situations. You make the ocean less acidic and you remove carbon dioxide from the atmosphere. So there are some, I think, innovative ways to do that. Frankly, it's way behind what other fields have been doing because of the concern about trash in the ocean. That, oceans are very fondly loved by everyone around the world. And the idea that you're going to use the ocean as a dumping ground, pretty anathemic to anybody. So it's taken a while to get people around to the idea that, well, wait a minute, it's happening anyway. We better figure out how to improve the situation rather than just turn a blind eye to it. I'm encouraged, but it's a good place for study. And I think there's some interesting new things going on.
Can you say a bit more about how you envision coordination with the state to get enough biomass to do this at scale?
So two of the big biomass sources are already aggregated. The agricultural waste is mostly at the plants that, like the almond shelling plant is where that comes from, or a rice hull plant, although rice is actually problematic, a lot of silica in that. So that's relatively easy. You just go out and contract, and there are 3 or 4 developers in the Central Valley right now who are going out and making those contracts with the agricultural sources because they're the best. Trash, there's a hydrogen plant being designed for Lancaster right now that's running on trash, and then this plant that I mentioned to you in Reno that's getting from waste management. So those are pretty straightforward. The hard one is the forest waste, which is about half of the material. And the state has looked at that, and there's a big working group. There's a multi-agency working group. We all know how well those go. But anyway, they're trying to understand how to improve the contracting. One of the things that they've looked at that I'm kind of fascinated by is to make a utility that provides this. And the advantage of the utility is that they would be allowed to enter into long-term contracts, whereas because of the current, particularly federal Forest Service rules, there are no long contracts available. So that's a problem the state's trying to solve.
Have you had any pilot projects to ensure CO2 does not have unexpected problems when pressurized and stored?
Yeah, that's the thing that we've worked on in the Department of Energy for a long time. That's what I've literally spent the last 25 years on. And 14 million tons have been put underground in those pilot projects. And yes, you do pressurize, and you have to be careful of that. But underground pressure is something that's pretty well understood from the oil industry. So we know how to do it, but it has to be regulated because there's a temptation when you're stuffing something underground to overpressurize it, which is what happens in Oklahoma, where they're using waste disposal wells, water waste, where they're disposing of things like acid waste and things like that, and they've pumped too much in there and caused earthquakes. So you do have to be careful of it. That's a very poorly regulated area right now because the EPA regulations haven't been updated for that like 50 years. But yeah, you have to be careful of that.
What's the status of commercial biomass to hydrogen technology like proton pyrolysis and hydrogen cogeneration technology?
All of those components exist independently. The only demonstration plant that I am aware of is a small one in Swindon, England, that is currently doing everything in that chain, going from biomass all the way through to hydrogen. There are a couple of significant plans to do that here in California, one in Lancaster, one in Bakersfield, another one in Paradise, the town that burned up 2 years ago. Interestingly, the plant that's the most ahead on all of this is a plant called Clean Energy Systems that's near Modesto. And they were originally going to do exactly what I described, make hydrogen. And then they figured out that they could make more money by taking the syngas and burning it and selling making electricity and selling that electricity to Tesla for its charging stations. And then you get the low carbon fuel standard credit. You get the $200 a ton for the CO2 by putting it underground. You have to put the CO2 underground to get that credit. And so they stopped making hydrogen and they're just making electricity. And they will be the first ones online probably 2 years from now, I would guess.
Another question is, waste incineration typically has to deal with dioxin. Is this a problem for gasification?
Well, it certainly is. And that's why I was so harsh on those two-stage gasifiers. You can't have a smokestack on these things. You know, a gasifier, the single stage one, reacts everything into carbon dioxide, hydrogen, and carbon monoxide, and then you shift it to make just hydrogen and CO2. So that would be a problem, and that is why we cannot permit those kind of two-stage gasifiers here in California.
There are a few other questions that I'm going to pose since we do have a few minutes left. Most power plants are near periphery or in middle of cities. Is the idea to drill at the plants for CO2 capture? Is there room to do this in the Bay Area or LA Basin, for example?
You probably wouldn't build the plant exactly on top of the storage area just for logistical purposes, but short pipelines can be done. Long pipelines can be done, but they're hard, we all know. The most likely places right now are in Bakersfield, to do it directly in Bakersfield, where there's terrific storage. There's almost unlimited geologic storage in the Bakersfield area. And then the other place that's really, really good is the delta between my home here in Livermore and Sacramento, that area, that sort of trackless waste out there that is built up islands. There's a lot of natural gas production out there, and that's a great place to do it. But you wouldn't build the plant in the delta. You'd build the plants up on dry land, you know, in Sacramento or Stockton.
Another question is, would using geothermal for electric generation prevent more CO2 release? How does electric generation compare with biomass conversion?
You've got to do both. You know, we have to replace fossil fuels, pure and simple. And geothermal is a terrific way to do that. And the question is, do we use our geothermal just for electricity or to do direct air capture? I think we need to do the demonstration plants and really decide how we feel about that. And we always turn these things in terms of money, and that's wrong. These things are going to be decided. The costs are very manageable and they're all about the same. They're going to be decided upon the impacts to the rest of us, land use, pollution, visual impacts. We'll have to see. And I think that's why it's exciting that we're working on getting a demonstration plant built down in Salton Sea. Try them out, see how they work, see what people think about it.
Another question, could the need for CO2 in the beverage industry be another way to consume CO2 instead of figuring out how to store it?
You know, that plant that direct air capture plant that I showed you in Switzerland, they sell their CO2 to Coca-Cola. That's good in terms of their business model. It's bad in terms of direct air capture because the CO2 ends up right back in the air. So, you know, I think this is a trade-off that these companies have to figure out. They need to be profitable. I like to say you don't move 1 billion tons of anything without companies that make money doing it. So we all have to be tolerant of them making money doing it, but hopefully they're going to find ways that are more permanent than Coca-Cola.
One final question. The questioner wants to know a little bit more about how the biomass solid waste is gasified. It turns into what specific gas?
If you take wood and heat it up to about 900 degrees C, it will naturally convert into carbon dioxide, carbon monoxide, and hydrogen, plus, you know, ash from the minerals that are still there. So those are the gases that are created by the gasification.
Roger, it's about 12 o'clock. This has been just absolutely fantastic. We have learned so much from your talk and look forward to continuing collaboration with you and LLNL. We are all part of the UC system after all. And
yep.
I think this is just the beginning of great collaboration between our two institutions.
Very good.
So I thank you on behalf of everybody at UCI and all those who listened to you and benefited from your wisdom.
Thank you very much. It was a delight.
Bye, everybody.
Bye-bye.
Thank you for being here.